Chapter 10.8 notes, vectors. This is page 8. We're going to kind of wrap up here with some application problems. You may need more examples. Don't hesitate to shoot me an email. We can set up some time to meet and take a look at some of the other examples or work through some of the homework problems. So let's start with example 16. We want the dot product of v sub 1, which is 5i plus 2j, and v sub 2, which is 3i plus 7j. Then we want to find the angle between them. So we know from the last page that the dot product is fairly straightforward. We got v sub 1 dot v sub 2. That's going to be 5 times 3 plus 2 times 7. 15 plus 14, which is 29. There's our dot product. We are done. The angle between them, we're going to go back to the last page and find that formula. We've got the cosine of theta is v sub 1 divided by its magnitude. So basically that's the unit vector in the direction of v sub 1. That's going to be dotted with the unit vector in the direction of v sub 2. Okay. I chose, as I was writing this, to use the vector form. So my v sub 1 is 5, 2. We're going to divide both of those by the magnitude of v sub 1, which I haven't found yet. So let's move that over here. Magnitude of v sub 1 is going to be the square root of the x component squared plus the y component squared. Let's take off this part here so that I can fit this in here. So 5 squared is 25, 2 squared is 4, 25 plus 4 is 29. 5 over square root of 29, 2 over square root of 29. If I were just using this vector, I would get that radical out of the denominator. Because I'm taking the dot product, I'm going to end up multiplying things. I'm just going to go ahead and leave it for the time being. So we're going to dot that with, let's see, we've got 3, 7. I need to find the magnitude of v sub 2. 3 squared plus 7 squared, which is 9 plus 49, which is 58. 58 I recognize as 2 times 29, so I might find that helpful in a little bit. Right now I'm going to leave it as 3 over the square root of 58, 7 over the square root of 58, and we want the dot product of these two, which means that the cosine of theta, this is an important time to not leave off the left-hand side. I don't want to just crank out this number on the right and think I'm done. We still need to find the angle that this is the cosine of, okay? So I have got, what have I got? I've got my x components multiplied together. So 5 over the square root of 29 times 3 over the square root of 58, sorry, plus my y components multiplied together, so 2 over the square root of 29 times 7 over the square root of 58. 5 times 3 is 15. At this point, I'm going to break that denominator down, and I'm going to go, let's do this over here, square root of 29 times the square root of 58, which is the square root of 29 times the square root of 2 times the square root of 29, 29. Just square root of 29 times 29 times 2, 29 square roots of 2, which I think might be a little more useful. Plus, I got 2 times 7, 14, over 29 square roots of 2. That denominator is going to look the same as the other one, which gives me, I got to move this out of the way. It doesn't want to make it any smaller. Okay. Which gives me 29 over 29 square roots of 2. My 29s are going to cancel. I get 1 over the square root of 2, which we're definitely not going to leave with that in the denominator now. And so I'm going to multiply numerator and denominator by square root of 2 over square root of 2. And we get the cosine of theta is square root of 2 over 2, which means inverse cosine of square root of 2 over 2 is theta. Theta is pi over 4, or 45 degrees. So there is a 45-degree angle between the two of these. So we've got the dot product up here, V1, V sub 1 dot V sub 2, 29. And we've got the angle between them. A little more involved than just finding the dot product, but that's okay. Example 17 and 18, you guys, those are both application problems. So unrelated to 16, we're not finding the dot product or the angle between them, but we do want to make sure that we know how to use vectors to solve application problems, okay? So example 17 asks us to find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle 30 degrees below the horizontal as shown. So like, what the heck? Lots of stuff going on here. So the picture's drawn here for you. Here's our airplane. Notice this, the magnitude of the vector labeled as 100. You guys, that's 100 miles per hour. So as we talk about the component form of the vector, keep in mind that is giving us magnitude per hour and direction. If you were applying this to a problem that was asking for, you know, where it is 5 hours later, you'd have to work through that and figure it out. Okay, so here's what I'm going to do. I'm just going to draw the right triangle in. Boom. Okay. I have an angle 210 degrees. I have the magnitude of the vector 100. So if we call this vector V, I have got this part, and then I know my theta is 210 degrees. So I am going to go back to page, I don't know, 7, top of page 7, where we want the component form of the vector in terms of magnitude and direction. So even if I'm a little uncomfortable with what's going on here, I know that I've got a magnitude of 100 and a direction of 210 degrees. And I can substitute that in. The cosine at 210 degrees, take a look at where we are and go back to what we know about that unit circle and position on the coordinate grid. We're in quadrant 3, so both my cosine and my sine are going to be negative. So my cosine here is negative square root of 3 over 2. My sine is negative 1/2. I get negative 50 square root of 3i minus 50j. I'm not going to worry about converting that square root of 3 to a decimal unless I need to. That square root of 3 is an exact value, and I would much rather have my answers in terms of exacts. Okay, and that's it. That's the component form of the vector. 18 is looking for something a little different. This time we don't have a picture, so I'm going to do my best to draw a picture that represents the situation. So first off, they tell me that the pilot of a plane points his airplane due south and flies with an airspeed of 120 meters per second. So I'm just going to start him at the origin, due south. Blends right in there. That's not helping. But I know that his airspeed is 120 meters per second. And just a reminder, south, north, west towards the mountains, and east. Okay. We also know that simultaneously there's a steady wind blowing due west, and I'm going to go head to tail on this. Due west. Sorry, wrong direction. Good thing I labeled everything. Due west at 40 meters per second. And so that force is working constantly on our airplane. Okay. And so our resultant vector is this one right here. Now, this is a right triangle. So for A, we have got that magnitude, magnitude of E, square root of 120 squared plus 40 squared. Once we crank that all out, I get 126, rounded up to one decimal place, 0.5 meters per second. So that wind does have an effect on our airplane. And keep in mind, we don't have any interaction. I don't have this pushing against the direction the plane is going, just straight west while our plane is heading straight south. But the result is that the plane is moving at 126.5 meters per second. Okay, and so now we want the resultant direction. And so we've got tangent of theta equals, so quick reminder, whenever we're talking about these triangles, that theta has to be made with the x-axis. So we are looking for where the tangent of theta is negative 120 divided by 40. Guess I should just write that instead of just saying it. So we've got a tangent of negative 3, which means we want the inverse tangent of negative 3, and that gives us an angle of negative 71.57 degrees. I'm going to round this to 2 places. So that means that this is negative 71.57. Let's try a different color here. So when we want the resultant direction, keep in mind that was from our 0 here. So 180 plus an additional 71.57, I get 251.57. Now there's one thing that I want to talk about because it is going to come up as we talk about section 10.1, and that is bearings. Okay, so when we talk about bearings, and this is just an aside, that question is answered. Our bearing starts with north and south. So we start with north and south. And I want to take a look at how many degrees off my vertical axis I am. So when I talk about bearings in terms of this problem, I'm going to start with south because I have moved south from the origin. And then I want the number of degrees away from the axis. So now I'm looking for this angle when we talk about bearings. So whenever we talk about directions or reference angles, it's all with respect to the x-axis. When we talk about bearings, we're talking with respect to the y-axis. And if I am, let's see, I got a negative 71.57 there. So I definitely want to figure out how far away that is from the y-axis. You guys, that 71.57 and this other little green angle are going to be complementary, which means they have to add to 90. So to find this angle, I'm going to go 90 minus 71.57, which gives me an 18.43 degree angle. So I'm at south, 18.4 degrees west, because we are going in the west direction. And we will talk about bearings more in the next section, but figured I'd throw that in here as long as we had a situation where it would work. And that is the end of the 10.8 notes.